Let's talk about mesh current method. We will do this using an example circuit. To understand this method, we will need two concepts: loop currents and branch currents induced by loop currents. So what are loop currents? We can pick any loop and say the current in that loop is something. So for example, I pick this loop and I say this loop current is I1. Branch currents are those which you're already used to. Branch currents are the currents which are flowing through individual branches. When you measure the current using an ammeter connected in series, what you're really measuring is the branch currents. Now we say the loop currents induce branch currents, and the way you calculate the branch currents induced will be, you say this: the current flowing through each branch will be the sum of all loop currents. So in this example, there is I1 flowing through V1, there is I1 flowing through R1, there is I1 flowing through R3, the same is flowing through V2, and the same is flowing through R1. But there are no loop currents flowing through R6, R5, and R2, and V3. So if I calculate the branch currents induced by I1, I get I1 here in this direction, 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 and 0 here, 0 here, 0 here, 0 here. Because at this point, there is no loop currents flowing through R5, R6, R2, and V3. I did not specify any direction for the zero currents because when the current is zero, the direction does not matter. But however, we can give them a direction. Again, it does not matter. Let's label all the essential node so that it will be easier for us to talk about the circuit. Now, if I want to write a KCL at B, let's see. So the statement for KCL is sum of all currents going into node B should be 0. So I will start from the left hand side, go anti-clockwise. So from the left hand side, current going in is I1. In the bottom, current going out is I1. And to the right, it's 0. And this should be equal to 0. So as you can see, this is satisfied. Let's write a KCL at node A. Again, going from left, and this time we'll go clockwise. So minus I1 going in on the left hand side, plus I1 coming in from the top, plus 0 from the right, and this is actually equal to 0. And similarly, you can verify that KCL equations at C will also be satisfied. If you think about it, this should be obvious. The way we're defining the branch currents are through loop current. And in a loop current, at any node, because it's a loop current, the current going into that node will be the same current coming out of that node. So the total current going into that node should be 0. This brings us to the first statement we will make. Branch currents induced by a single loop current satisfy KCL equations. Now let's see what happens when we consider two loop currents. The first step again would be to figure out the branch currents induced by these loop currents. Okay, so first I will assign the branch currents induced by I1. So that will be, let's pick the right color. So that will be I1, I1 in this direction, I1 in this direction, and I1 in this direction. And contributions from I2. So this will be plus I2 in this direction, I2 here, I2 here, and I2 here. And since there is no loop current going through R6, the current through R6 will be 0. So let's write a KCL at node B. Starting from the left, going in anti-clockwise direction, I1 going in from the left, minus I1 plus I2 going out in the bottom, plus I2 coming from the right. So this should be equal to I1 minus I2 plus I2, and this will be equal to 0. If you notice in this expression, I can write this as I1 minus I1 plus I2 minus I2. So this here is the contribution because of the first loop. This here is the contribution because of the second loop. Which brings us to the next statement we will make. The contribution of current at any node will be the sum of contribution due to each loop. And this is the key to how mesh current method works. By expressing the branch currents as those induced by loop currents, mesh current methods make sure that KCL equations are automatically satisfied. I would encourage you at this point to pause the video and in this circuit, add the extra loop current I3. Calculate all the branch currents induced by all these loop currents and make sure that the KCL equations are satisfied. And at each node, when you write, at each essential node, when you write a KCL equation, make sure that you can express the equation as sum of contributions of each loop current. Going back to this statement, since the mesh current method makes sure that the KCL equations are automatically satisfied, we only need to worry about the Kvl equations. Let's take the same example again. This time I have indicated all the loop currents, and I've also indicated on each branch the branch currents induced by these loop currents. I see three variables here, I1, I2, and I3. That means I need to write three KVL equations in order to solve the circuit. Note that if I calculate I1, I2, and I3, I know the branch currents in all the branches, hence solving the circuit. So let's write a KVL equation in the loop corresponding to the loop current I1. Start at that point, end at that point, going in clockwise direction. So going up, I have an increase of V1 plus I have a drop of R4 times I1 minus I3 plus I have a drop of R3 times I1 plus I2 plus I have another drop of V2 plus I have another drop of I1 times R1, and that should be equal to 0. That is my first KVL equation. I'm going to write the second KVL equation in the loop corresponding to the loop current I2, starting at essential node A, going clockwise. Okay, first when we go up, there's a voltage increase of V2, then there is a voltage increase of R3 times I1 plus I2, then there is a voltage increase of R5 times I3 plus I2. There's a voltage drop of V3. There is a voltage increase of R2 times I2, and this should be equal to 0. Let's write the third KVL equation corresponding to the loop of I3. I'm going to start at essential node C, going clockwise. First, there is a drop of R6 times I3. Then there's another drop of R5 times I3 plus I2. Plus there is an increase of R4 times I1 minus I3, and that should be equal to 0. Now, as a reminder, if you do get confused about increases and decreases and drops, all you need to remember when you're writing a KVL equation is sum of voltage drops along the loop is equal to 0. So I'm going to redo the KVL equation for the third loop, and this time instead of talking about increases and drops, I'm just going to talk about drops. So going clockwise, I'm going to sum up all the voltage drops and equate that to 0. Starting at C, going clockwise. Voltage drop from left to right across R6 is R6 times I3. Coming down, voltage drop across R5 from right to left is R5 times I3 plus I2, plus voltage drop across R4 from right to left is R4 times the current from right to left, that would be minus of I1 minus I3, and that should be equal to 0. So now I have three equations and three variables which I'll be able to solve, and that's mesh current method.